Seriously, thermal design is actually more important than radiation design. You're in daylight at a 10,000 degree Kelvin object called the sun. And on the night side, you're pointing at a 4 degree Kelvin universe. So enormous temperature differentials, and you have to account for that. I eventually sold the patent to Northrop Grumman, and that's what they built their business using the mission extension vehicle, which is the first practical commercial on-orbit servicing system. But now we're in a completely different world. So let's kind of explore it from that perspective.
Welcome to Space Terminal, the show where we sit down with founders defining the next century of space infrastructure. I'm joined by Dennis Wingo, founder of SpaceBilt, a space avionics and robotics player extending spacecraft longevity. Our listeners are leaders, operators, officers, and partners building frontier technologies. So Dennis, welcome. You're extending the lifespan of space systems. Why in space servicing? Why are other approaches sequestered?
In-space logistics was actually one of my earlier ventures. I was very fortunate to spend 10 years in research at the University of Alabama, Huntsville, mentored by some of the original German rocket team and the Apollo era scientists and engineers that took us to the moon. It's a terrible historic failure that we did not go forward with this, because many of the things that we talk about today regarding in-space logistics, what we call now ISAM, or in-space assembly and manufacturing, were pioneered back then. There was a classified 1958 report called the Horizon Report. From then, the Army Ballistic Missile Agency, Dr. von Braun was the lead of that, regarding going to the spacecraft that would take humans to the moon in low Earth orbit, have 18 crew people, and go to the moon from there. If you look at the original law that approved the space shuttle, there was actually multiple elements. There was the space shuttle itself. There was also the orbital maneuvering vehicle, which would have been used in low Earth orbit to go out and capture satellites and bring them back to the space shuttle for servicing. There was also the OTV, or orbital transfer vehicle, that would have taken satellites from the space shuttle itself all the way to geosynchronous orbit and then brought back to the Earth for servicing and reflight. Fully reusable. There was another final element called the Flight Telerobotic Servicer, or the FTS, and it was a robotic system to be able to enable in-space servicing. The only part of that had ever survived on the space station today is the robotic system that they use for assembly and servicing. 2001 was a terrible year in aerospace. Several internet constellations that had been proposed in the 1990s, all of that crashed and burned with the dot-com crash and the telecom crash, which was actually bigger than the dot-com crash. At that time, I was working with this fellow who was a billionaire about what can we do in space. And this was a fellow that had rented the Mir space station for a year, wanting to turn that into a commercial destination. We're sitting in the offices of Aon Insurance in Washington, D.C., and we found out that the French government at that time was underwriting their company, Thales, to build satellites cheaper than we could. And we were partnered with the Russians back when we were friends with Russia to build geosynchronous satellites very cheaply in Russia. But the French government was undercutting that. And so we said, okay, what can we do that's not a science experiment? How can we make money? And we looked at life extension. That was the idea that we came up with there in the offices of Aon Insurance in Washington, D.C. We developed that. I wrote a patent, and through many tangles, toils, and snares, I eventually sold the patent to Northrop Grumman, and that's what they built their business using the mission extension vehicle, which is the first practical commercial on-orbit servicing system. That's kind of the preface of where we're at today but now we're in a completely different world. So let's kind of explore it from that perspective.
Back to the new world, to today, you're building a logistics robot and a 500 terabyte server. What's the strategy here?
It's a commercial roadmap. A lot of my background is in design and test engineering in the computer industry and also in the space industry. Prior to literally just a few months ago, many of the things that I have talked about in space servicing and building vehicles in low Earth orbit and advanced computing in space were considered anathema. Really, I'm only 35 years old, and most of my white hair comes from trying to convince NASA and the Defense Department to do more advanced compute in space. Since after the Apollo era and rapid advance of technology in the computer and the space industry diverged from each other. I flew the first Macintosh and the first hard drives in space on the space shuttle in 1992 as an experimental payload. And literally, we were told that no possibility that it would work. We flew a Macintosh running LabVIEW, standard software, and the experiment worked. Aerospace computing, until just the last very few years, have been using 35-year-old technology. And with Elon Musk's success in flying Starlink, I actually worked with the previous incarnation in the 1990s, Teledesic, partly funded by Bill Gates, and it failed. I've been spending years, the past 20 years, slowly building credibility, flying payloads, showing that, yes, this computer will actually work in space. I can actually fly an SSD drive in space and it doesn't spontaneously combust or vaporize or radiation destroyed or whatever. And so now with advanced technology, and you've seen literally in the past 60 to 90 days, Eric Schmidt, Elon Musk, Bezos, we're going to build all these 1 gigawatt data centers. They've got to back up to reality. We're delivering a 500 terabyte server in March that will fly in July to the International Space Station. We're following that with a collaborative activity with Axiom Space. We're flying another server to the space station in November, and in March of 27, we are going to be the first multi-laser constellation node in space at the International Space Station, proving these technologies and providing the engineering basis for what all these guys want to do.
ISS will retire in, say, 5-6 years. We're going to see space habitat nirvana as well as the data center nirvana. Who are your customers? Who's putting the purchase orders for these constellations that you're building?
The U.S. government has seen fit that we have to get beyond our and I will use the Eisenhower term, our military industrial complex had gotten so overwhelmed by their own paperwork that advancement was becoming extremely difficult and extremely high prices. And then in small satellites, Elon has picked up, you have great constellations like Hawkeye 360 and Signals Intelligence, Umbra and Radar, Planet Labs and Optical. They're using a completely different business model, all predicated by the reduction in launch costs. Launch costs were still where they were 30 years ago, this wouldn't be as possible. Instead of paying $10,000 a kilogram, I'm paying $1,000 or maybe $3,000 a kilogram. It makes it more economically viable, which makes it more viable to take risk in computers, which makes it more revenue. And there is an old saying that revenue scales directly proportional to aperture. In space, you got to have power. You got to have antennas. That's the 2 ways you make money. Or an optical, that's still an aperture, an optical aperture or an infrared aperture or an antenna for signals intelligence like Hawkeye 360. Everything scales with that. And with the internet now, it becomes much easier to distribute this data. And ground infrastructure is actually much more of their cost than the space segment. And so we call this a systems of systems engineering problem, which means if you've ever seen the Drake equation about SETI, but you see all these 15 variables, well, the same thing is true in commercial space. And you have to balance all these variables. And at the end of the day, hopefully there's a kaching and you can make money on it. And there's some people that like what Elon's doing in space. This is what Televisic wanted to do in the 1990s, and we just weren't there yet. The other word for nirvana is utopia. And that was a book written by a fellow by the name of Thomas Mann. But that book was not about reaching utopia. It was about the futility of reaching for utopia. The plans that we're seeing right now, people are going out and raising money for it and all. We have some fundamental industrial limitation. If you look, Elon satellites are getting bigger and bigger and bigger. Started out, they could fly 60 on a Falcon 9. Now it's 24. Now they're starting out with 60 on Starship. It's going to go down to 30 because you need more power, you need more computing, you need more antennas to reduce what's called the price per bit. In space, this is the key metric, reducing the price per bit, which closes the competitive gap between space and terrestrial communications infrastructure. That's actually what Starlink is doing. And in many, many areas of the world, Starlink is way cheaper than the terrestrial infrastructure. And so that's where they have a competitive advantage. And then as their customer base grows, their cost per bit decreases, makes it more cost effective to build these bigger satellites, which creates this virtuous circle that changed the world.
How do you become profitable?
By sacrificing goats on the Friday. Profitability is always a key metric. Now, I just read a report on terrestrial data centers by Silicon Valley Bank. It says right now, all of these AI data centers are spending $5 for every dollar of revenue. Space data centers are going to be even worse. One of the things that's starting to happen with terrestrial data centers is local opposition and increasing energy prices and the limitation of our national grid. It's been said that we need to triple or quadruple the entire American grid to be able to handle the energy requirements of a data center. And so that's a problem. The current administration, the United States government is going to finance 10 what's called AP1000s, which is the Westinghouse 1 gigawatt or I think it's 1.2 gigawatt nuclear reactors. This is the biggest block buy of nuclear reactors since Richard Nixon was president. The United States between 1968 and 1972 licensed or started 45 nuclear power plants. But the nuclear scare of the 1970s put an end to that. There was actually a plan by President Nixon to build 1,000 nuclear power plants by the year 2000, which would have completely decarbonized the American electrical grid. Can you imagine how much different the world would be today? But it takes time to build nuclear power plants. We have to rebuild our grid. We have to do a whole new grid to handle the data center loads and tiny technical problems with that approach in that you got to build a gigawatt of solar power. And the problem is, and this is what Elon, and I'm going on public information here, Starlink is using terrestrial solar cells, silicon cells, for their spacecraft. But those don't last very long in space. But if you actually own a launch vehicle company, it becomes much more viable to launch new satellites all the time. The problem is if you're going to build a 1 gigawatt data center in space, it takes time. Right now, I don't care if you launch a Starship 3 times a day, it's still going to take, years to build a 1 gigawatt data center in space, partially because in space, in communications, if I build a geosynchronous telecommunications satellite, some of the big ones are like 20 kilowatts of power. Well, half of that electrical power is radiated as electrical energy to the ground in radio waves. They only have to dissipate half that heat. For a data center in space, if I build a 1 gigawatt data center, you only have 2 ways to move heat around. It's called conduction and it's called radiation. You don't have convection like on the Earth. And all those big cooling towers, those are convective cooling towers, which uses differentials in atmospheric pressure to be able to move heat up into the atmosphere and from water and all that good stuff. You don't have that in space. And there's fundamental physical limitations based on thermodynamics. This is basic equations of the universe and how much heat you can get rid of. For every, a good metric is for every 350 watts of electrical energy that you're dissipating, you need 1 square meter of radiator. If I have 1 square meter of solar panel in space at 20% efficiency, which is typical silicon, in space it's 1,350 or 1,360 watts per square meter. So now, if I have a 20% efficient solar panel, that's about 320 watts. Well, that's very close to 350. So to build a gigawatt of solar power, I have to have area to where I'm receiving, 5 gigawatts of solar energy. So I have to dissipate that 5 gigawatts, or 4 of that 5 gigawatts of energy radiated as heat. Well, we can do that. We've been doing that with solar panels forever. But for a data center, you got to radiate. So you take that other 20%, you also got to radiate that as well. And it's 1 square meter for every 350 watts. So if I have a 1 gigawatt, I've got to have square kilometers of solar panel. I have to have square kilometers of radiator at the same time. So we're talking enormous. Starship gives you a lot of volume, but there's only so many Starship launches you can do a day. And so if I've got Eric Schmidt over here trying to build a gigawatt, I've got Elon over here building gigawatts, I've got all these people trying to, you can see the logistics issue that we have. A fellow from NASA, his name is Dr. John Mankins, who was a space solar power advocate. Dr. Mankins was looking at beaming solar power with a 1 gigawatt power installation. It's a very similar problem to the space data center issue. And he talked about how much money do you have to spend to get to your first dollar of revenue. If you use net present value calculations, then you got to look at cost of financing. And so it is my opinion that space data centers, they're going to start out much smaller. And even Elon's talking about this, and he's shown pictures of their much bigger satellites. But you're going to have them support existing types of businesses in space or new businesses in space. You're going to need better communications, and now laser communications is helping that. But we're just at the beginning of this roadmap. Now, going back to an earlier question that you had, who are our customers? Right now, we're working with the Department of Defense, where we designed and built and flew for a commercial customer, the world's first data center that went to the moon. There is a lot of interest, and I'm well known enough that I built a lot of good hardware in space that they know that if they buy from me, it's got a pretty good chance it's going to work.
So I'm going to switch gears with a rapid fire. Rank these variables, and these variables are related to in-orbit servicing, assembly, and manufacturing. From 1 to 4, 4 means mission critical in 2026.
Okay.
Radiation hardening.
Depending on how you do it, a 4. And I have to expand on it slightly. The way we've traditionally been doing it, which is at the chip level, is no longer viable. The semiconductor industry didn't give a crap about the space industry from that perspective, except in limited circumstances. Shielding is going to be done in a completely different way in the future because we have to use commercial components, or at least automotive components, because the price differential between a rad tolerant or a rad hard part and a commercial part is just so astronomically wide that it's not financially viable to use the traditional methodology for radiation hardening.
Okay. Cooling orbital data centers.
5. Thermal design is actually more important than radiation design. One of the key failure mechanisms in space is thermal cycling. You're in daylight at a 10,000 degree Kelvin object called the sun, And on the night side, you're pointing at a 4-degree Kelvin universe. So enormous temperature differentials. And you have to account for that. We've done things that NASA said couldn't be done. We rescued a spacecraft that had been in interplanetary space for 35 years called ISEE-3. NASA allowed us to do this, and we did it privately. And we were able to analyze the engineering systems on board the spacecraft. And remarkably, over 90% of this spacecraft was still fully functional after 35 years in interplanetary space. And the temperature on board the spacecraft was within 1/2 degree from the best predictions that the engineers had made. These guys didn't have supercomputers. Thermal stability. If I were to chart it, on your chart, literally it's at the top of the list. It's even bigger than radiation.
To your earlier point about legacy rad hardening and the limiting factor being funds, similar for thermal management, what's the limiting factor right now?
For thermal management, it goes back to our Aperture thing. The cost of a spacecraft is an exponential function of Aperture. And Planet Labs build their doves, which are little 3U CubeSats with an 80-millimeter aperture. Well, those spacecraft are super cheap. The Hubble Space Telescope with a 2.4-meter aperture costs, like $3 billion. And the James Webb Telescope with a 6.5-meter aperture costs as much as a Nimitz aircraft carrier. Viasat was a geosynchronous communications satellite, Northrop Grumman, and NASA helped support it to build a big antenna for their internet over satellite. That antenna failed, about 8-meter in diameter antenna. And when that failed, it cost them $400 million. The rest of the spacecraft was fine. This is what drove us towards in-space assembly and manufacturing. The insurance industry is very supportive of this. They don't like paying out claims. They had to pay out a $400 million claim on Viasat. And whether it's thermodynamics, radiators, solar panels, RF antennas, or laser optics, that is the key element that in-space assembly and manufacturing helps you bridge. If I build a satellite here on the ground and I launch it, I have to do most of my engineering and most of my qualification for an environment that the satellite sees for 10 minutes. We have some really good computational code for that, but the problem is the mechanical engineering. There's a function, famous German rocket scientist, Dr. Ernst Stuhlinger, who was one of my mentors, they call it the U-shaped curve. Overhead for building something very small is high, but as I go this way on the U-shaped curve, there comes a point to brings the cost down to a point where your profitability is good. As you get over here to the other side of the U-shaped curve, if I'm building something really big, those costs really start to rise exponentially. Mechanical engineering for the deployment of thermodynamic systems is the cost driver.
Understood. Let's talk about orbital servicing and assembly at scale. The use cases you brought up are bespoke one-off missions. What's the path to reliable cadence?
I like that term. Both Elon and Jeff Bezos are solving the most important part of that equation, rapid, low-cost launch. Elon, if you're watching this, hi. Whether it is the Blue Origin with Jeff or Starship with Elon, all of these systems or what is called volume limited. There's an old saying in the South, some people try to cram 10 pounds of cow dung into a 5-pound bag. There's a metric, it's been around since von Braun, that you can have reusability, but it takes about 1/3 of your lift mass. And if you run the numbers on Falcon 9 or Starship, you'll see that the fuel that they have to carry is about 1/3. It takes away about 1/3 of the launch mass. That's okay because I can't stuff enough inside of this 8-meter volume for Starship or 6.4-meter for Jeff Bezos to fill up the mass margin. So it's okay if I'm wasting 1/3 of my mass margin on fuel and get reusability and lower the cost there by increased cadence. And so the cadence of launch, and the next on that is how do we do these in-space assembly facilities, which is what we're working on. We use the term, how do you Henry Ford-ize space? Henry Ford changed the world with the assembly line. And what his premise was is that I want to bring down the cost of an automobile to where the guy working on the line building the automobile can afford to buy one. That also was true in the railroad industry. My great-grandfather worked on this in the railroad industry to bring costs down in railroading in the 19th century to bring the cost of transportation down. Henry Ford did this in the automotive industry in the early 20th century. Elon, it is my premise that to reap the ultimate advantages pertaining to scale and mass production of large space systems, which is what we need for data centers or a plethora of other applications in space. We have to move the factory into space.
Speaking of factories in space, in Moonrush, you posit a lunar economy around platinum group metals. In 2026, is this sci-fi or reality?
Well, it's actually less sci-fi than it was then, but my thoughts have evolved since I wrote Moonrush. People talk about the killer app in space. Another term is a silver bullet. Using silver bullet to kill a vampire. Communication so far has vastly dominated space, but we have to go beyond that. The famous Russian writer Tchaikovsky wrote, "The Earth is the cradle of humanity, but we can't stay in the cradle forever." If the limits to growth crowd is that we do have limited resources here on Earth. The limit is energy. If a megawatt of electrical energy was as cheap as a kilowatt is today, we could process raw granite from the Sierras, and the waste product would be oxygen. And so it's an energy equation, as it has always been for humanity. There's a graphic that shows wealth of nation versus energy use, and there's no such thing as a low energy use wealthy nation. Our thinking has evolved in that if you do the studies, and we're working with a group right now to formalize some of my more ad hoc studies, is that there's multiple trillions of dollars worth of industrial production on Earth that's dependent on vacuum. It is now my premise more, and platinum group metals still figure into this, the moon in low Earth orbit, the vacuum is about 10 to the minus 5 Torr, because there's still residual atomic oxygen at the space station altitude. On the moon, it's 8 orders of magnitude more vacuum. We use vacuum for so many processes, especially for advanced ones where impurity levels have to be very, very low in the parts per trillion. And high vacuum is the way to do that. Here on Earth, high vacuum has its limitations in terms of how good you can get a vacuum. On the moon, you have 10 to the minus 12 Torr, enormous vacuum, because it's completely outgassed for billions of years. Here on the Earth, we use vacuum entirely in what's called batch processing. I have this, I put it in a vacuum chamber, I draw the vacuum chamber down, I do whatever I'm doing, I come back to atmosphere and move it out. That's called a batch process. Guess what? I can go to continuous processing, and there's a plethora of materials technology, and the moon, which is basically a big rock that's made out of metals and oxygen. You can extract those metals, and guess what? Oxygen is your waste product. Guess what I need for propulsion? I need oxygen. There's even a propulsion concept that uses aluminum as fuel and oxygen as the oxidizer, which would, without having to worry about finding the rare hydrogen and water in the polar regions, to be able to do propulsion. So it's more of, again, it's a gestalt, integrated system. But what we need is the investment, whether it's private investment or cooperatively with the government through public-private partnerships. And we did the same thing with the semiconductor industry. It was the U.S. Defense Department and NASA that created the semiconductor industry. 1965, the U.S. Defense Department and NASA accounted for half of world production of semiconductors. They paid for the production lines, early production lines in semiconductors, to where it got to a point to where after Apollo, it took off on its own. We want to get out of this situation that we have today. It's going to lead us to war if we're not careful. Why did Russia attack the eastern part of Ukraine? That's where the resources are. It's where the coal's at. It's where the iron's at. It's where the gas is at. And if you take a look at the global competition for resources with our friends in China, our friends in India, all over the world, what does each country need? They need raw materials. Where do the raw materials come from? Africa, South America, what's happening in Africa. All of these areas are in chaos because of the scramble for resources. What if we had a resource base that was 1,000,000,000,000 times larger than what we're fighting about here on the Earth? It would tend to lower the temperature, driving us towards war. And economic competition and going out into space is one heck of a lot cheaper than war. Platinum group metals, there's titanium, there's all these metals and processes and industrial activity, not only on the moon is where we start, we go to Mars as well. And you see the tagline in my book, we go to Mars to take our civilization. The archaeology and paleontology tells us that humans have been around for 300,000 years. We've only had civilization for 10,000. Rome is what I call a type 1 industrial civilization, but we've only had real industrial civilization for 300 years. We're running up on some limitations, but we have a solar system that is so incredible. If I was designing a solar system for Sims, I would design a solar system exactly like what we have now. Let's go out there and have fun rather than fighting about in the little sandbox here.
Speaking of interplanetary travel or in-orbit maneuverability, what are some design decisions or some systems engineering decisions that helped you master LEO, GEO, and future cislunar environments? Because you have a DIU contract for GeoBirds, but you're also working in LEO with the Axiom partnership that you earlier mentioned.
Well, I'm able to take it one step further because we have a gravity well in physics. It's called Hamiltonian dynamics. The top of the gravity well is up here, and that's about 1,000,000 miles out. And we're on the Earth at the bottom and in low Earth orbit, and you start climbing. Buzz Aldrin, second man on the moon, had an idea for what's called an Aldrin cycler. And you've seen the movie The Martian. That interplanetary vehicle to me is one of the coolest things in the whole movie because it kind of sort of looks like the space station, but you can tell there's no possible way that thing got built on the Earth and then launched. It was designed and assembled in space. And so I can build not only cislunar cyclers, fully reusable cislunar cyclers, because Elon doesn't have that. Jeff Bezos doesn't have that. My friend Tom Mueller is talking about the very beginnings of that. But if I can do in-space assembly and manufacturing, I can build an interplanetary in space. And I can put a nuclear power system on it and nuclear propulsion. And so now I have a truly reusable interplanetary vehicle that allows me to go to Mars, to the asteroids, that allows us to start opening up the solar system and to our robotic friends, because, robots in the future are going to do 90% of the work. But if we have this infrastructure in place, we can build nuclear propulsion systems. Most people don't know, during the Apollo era, Dr. von Braun and the team at Marshall and the Atomic Energy Agency built a nuclear-powered third stage for the Saturn V. That would have doubled the payload of the Saturn V to the moon. The Saturn V of the 1960s could put more payload, even though it's half the thrust, to what's called translunar injection than Starship can, because it used high energy propellants. The Apollo 17 was 58 tons to translunar injection. And that didn't include the third stage, which was with it as well. The NERVA third stage would have increased that to over 100 tons. And that's what Starship's putting into low Earth orbit. So with nuclear-powered propulsion, we literally liberate humanity from the Earth. And that's what in-space assembly brings you. So it's a virtuous circle on the roadmap to nirvana.
So this utopia, how big is it? How do you quantify this market?
In-space robotics help you build much bigger aperture. You're going to have that for in-space data centers. What Elon is talking about doing is using his mass production capabilities here on the Earth to do that. We're doing that as well, but we'll do it in space and connect our vehicles in space to build bigger ones. But you have to crawl before you can fly. The Model T had to be built before the Tesla was. And so we're just at the beginning of this. And so we have to be able to make it profitable. And the United States government, for decades, incentivized the contractor community because it was called government allowed profit margins, or like 7, 8, 9%. So how do I increase my profits? I have to increase the cost because I get to layer 7 to 9% on top of whatever my cost. That's how you get the space launch system. It's $5 billion a launch to the moon. But we can't do that if we're actually going to move into space. What the railroads did, what Henry Ford did, what Elon's doing, we got to bring the cost down. And in terms of applications, talk about real-time crop monitoring with hyperspectral imaging. Compute, you need storage, you need communications to do that. If I'm going to monitor the oceans for illegal fishing, if I'm going to watch traffic en masse, and, here's a rain cloud coming. Your commute over here on I-94 in Chicago is going to get rain in 5 minutes. In space, you can start to bring the cost down in aggregate in a manner to where it makes weather prediction better. It makes crops monitoring better. It's incremental building. It's getting past plateaus and heading up the exponential curves that we have done in the semiconductor, with the internet, all of these things, all of our advances in human productivity, and it is counterintuitive to what you see on the internet. It's not sucking the last dollar out of everything. It's bringing the cost down to scale so that more people can afford it, so the economic activity increases.
You're openly biased towards testing. I'm curious, where do you see the next evolution in avionics testing and testing for semiconductors or servers? Is there a use case in orbit? And how does it beat Earth vacuum chambers?
Terrestrial vacuum chambers are always going to be our first line of defense, because it doesn't matter how good the simulations are. They're still dependent on the simulators. The simulators might make a wrong assumption. I have a really good friend, an astronaut, Pierre Thuot. And Pierre did the Intelsat 6 rescue using the space shuttle in 1992. They spent an enormous amount of money developing this stinger that's going to stick in the apogee motor of this geosynchronous satellite, and it's going to capture it, bring it to the space shuttle, bring it to Earth. What happened on the end of the space shuttle robotic arm? And the video, he grabbed the satellite with his hands, and he used his muscles to stop the rotation of that satellite so it could be captured. So human ingenuity is the saving grace. We're always going to make mistakes. And so having vacuum chambers here on the Earth, whether they're small ones, huge ones, the beam lines and the radiation testing facilities are always a huge limitation right now. It's actually cheaper sometimes just to fly something and put a radiation sensor on it and see what happens. Some of the methods that we're using today are not appropriate for the environment in which these systems actually operate. And so we're getting misled. There's no substitute for putting it up in the environment if you can afford to do so. Intuitive Machines flew the payload to the moon. We had a radiation detector on that payload. And so we monitored the radiation environment on the solid state drives, on the CPU, and you can model that all you want. You can test all you want. It doesn't equal the environment that you're actually going through, because the environment is so different. It went through the radiation belt, outside of the magnetosphere, all these different environments. It's very difficult and expensive to pay for that. I can't tell you exactly how much I paid, but it was cheaper than the testing. Send the radiation to the moon to monitor the health of that payload for a commercial customer. And it takes that data and it informs us for designs in the future. So we're almost at the cusp to where it's cheaper to just send stuff to space.
Because it almost sounds counterintuitive, like we should test it first because launch costs are exorbitant.
But they're not as exorbitant as they were today. The cost is so much less expensive now to where adding a radiation sensor is trivial.
You've lived through capital collapses at Orbital Recovery, Iridium. What are some lessons that you carry forward today on liquidity management?
The lesson is only the insane survive. The geosynchronous communications market. And then there was a fellow that with his own money, launched it and created a company called PanamSat that broke the monopolies of the government. I wrote the very first paper on building internet over satellite in 1989 for IEEE. And in the 1990s, people thought it was insane that Teledizic wanted to build 544 satellites. What killed it at that time was the economics. It was the dot-com crash and the terrestrial telecom crash. But you have to be persistent, have to be willing to challenge your own assumptions. You have to be willing to maybe take side roads that aren't directly in the path of where you want to be. I've been in the Cro-Magnon era of space. It's going to get a lot easier based on just economics and testing and follow through and understanding space going forward. And our generation, the last 35 years, have taken the slings and the arrows. We've been out there trying to slay mammoths, and where the folks in the future are just going to be able to tend cows. And that's a great thing. And it's maybe the legacy of our generation is that we were too stupid to give up. I sat down with Elon when he first started SpaceX. Elon's gone so much farther down the road than what we even talked about. We need visionary capitalists in this business. And Elon would never be where he's at today if it hadn't been for folks like Steve Jurgensen, Peter Thiel, Founders Fund, people like that trusted Elon, that trusted that he was doing it, but also on the government side. I had dinner with Tony Tether, who was the head of DARPA, and after Elon's fourth failed launch, even while the buildings were still smoking at Kwajalein, Tony Tether called up Elon and says, "I'll buy your next launch," which gave the investor guys the confidence to throw more money in. There's a comic that shows these two professors at a blackboard, and you see all these equations on one side, and you see all these equations on the other side. Well, in the middle, there's a little bit of text that says, "Then a miracle occurs," and then the equations close. That's how we used to talk about space. Space tourism used to be laughed at until we started hitting these inflection points and all. And so it's about persistence. It's about learning your art. Just as 500 years ago, the best katanas in Japan were made by the people who understood their art.
Dennis, you're a man of art and a man of firsts. What should we look forward to from you and SpaceBilt over the next 3 months?
Well, we're delivering the payload in March to go to the International Space Station. That will be a 500 petabyte server. We have multiple initiatives going forward with customers. Our laser communications demo, we're close to critical design review on that. It's like what I'm talking about. You start building momentum. You don't really see the progress when you're at the bottom of the exponential curve, but we're starting to scale. We hope to be able to announce some of the things we're doing to scale our activities in the next few months.
And how can satellite operators, orbital data centers, and government partners contact you or SpaceBilt?
Well, I'm easy to find. Wingo, WINGOD at SpaceBilt.com. We're about helping to build the ecosystem. I think the next few years are going to be some of the most exciting years in space since the dawn of the space age.
This has been Space Terminal. I'm Zuni from Imagining Forward. New space episodes out every week. You can find Dennis Wingo and SpaceBilt in the show notes. You can also look up SpaceBilt on our intelligence tool at imaginingforward.space.
Thank you.